For decades, classical software has relied on deterministic rules. Code executes as a strict sequence, reliable for known tasks, but fragile against unstructured data. Generative AI chatbots represented the first major attempt to process this unstructured data at scale. However, standard chatbots suffer from a fundamental architectural limitation. They are passive and stateless, built only for single-turn text generation. This single-turn response mechanism cannot handle the multi-step dynamic complexity found in actual enterprise workflows. Without the ability to maintain state or self-correct, chatbots lack true agency. For autonomous enterprise execution, they are essentially dead ends. Moving from basic generative AI to agentic AI requires a shift in how we structure execution. Autonomous agents are stateful digital workers capable of continuous execution. In this model, the single-turn prompt is replaced by a continuous, self-correcting spiral. This spiral relies on two properties: persistent statefulness to remember previous steps, and dynamic error correction to adjust the plan in real time. To understand these agents, developers must stop viewing the large language model as the complete application. The LLM is merely a central processing unit operating within a broader system architecture. Building true AI autonomy requires moving past prompt engineering to focus on classical systems architecture. The definitive mental model for this approach is Andrej Karpathy's LLM as OS framework. We can map this framework directly to the classical von Neumann architectures that established the baseline for modern engineering. In this system, the foundation model functions strictly as the CPU. The system prompt acts as the instruction set, driving the CPU to process logic and make decisions token by token. The second component, the context window, functions as volatile RAM. This RAM stores recent history, active tool returns, and the immediate state data required to complete the current task. However, this RAM is constrained by strict token limits. If the context window overflows, the agent loses its active state and the task fatally crashes, exactly like a physical computer running out of memory. To address these RAM limitations, the architecture requires persistent storage. This is where the vector database serves as the file system, or the disk. Retrieval-Augmented Generation, or RAG, is simply a disk read operation, pulling historical data into the context window RAM as needed. But even a CPU with RAM and a disk is still sandboxed from the outside world. The final components are the APIs, which function as the I/O peripherals. Tool schemas act as the device drivers, teaching the LLM CPU how to format programmatic requests for external software. This hardware architecture provides the persistent memory and physical reach that a naked LLM lacks. With the hardware OS built, we need a software kernel to manage the execution cycle. That kernel is the REACT loop, standing for reason plus action. To see why REACT is necessary, we have to look at how reasoning-only architectures fail. Reasoning-only systems often hallucinate because they lack the external I/O access required to verify their own logic. Conversely, acting-only architectures, or direct API integrations, face a different failure state. These systems often trigger API calls in endless loops because they cannot evaluate a logical plan. The REACT framework interleaves these two extremes into a single pathway. It requires the model to formulate a thought before triggering an action, and then observe the result before reasoning again. This kernel is the essential stabilizing mechanism that prevents the system from crashing into infinite loops or confident hallucinations. We can now see the REACT kernel in motion through a practical task. A user provides the objective: calculate 15% tax on a $24,500 salary. In step 1, the agent formulates a mathematical plan in its context RAM. This is the thought phase. Step 2 is the action. The agent maps that plan to its I/O driver and triggers the calculator API. In step 3, the observation, the external API result returns directly into the context window. The cognitive loop then checks this new observation against the original thought plan. Instead of guessing, the system dynamically updates its plan based on the new state data. By watching this process, we see that this explicit logging turns abstract token generation into transparent, stateful, and highly predictable programmatic action. Here, we see the entire system operating holistically. React continuously queries the LLM CPU, manages state and context RAM, reads from the vector disk, and triggers API peripherals. The loop continues until the internal reasoning confirms that the high-level user objective is satisfied. Once the task is complete, the system saves its final state and powers down to a standby mode. This represents a fundamental shift in enterprise strategy. Deploying autonomous agents does not require training massive new models. It requires architecting robust state management and strict tool schemas around the models we have today.